push it to the surface. This is what it looks like. So the current will be mostly on the surface of the metal, and down, deeper down into the metal, it will be less and less. And this effect is actually used for shielding. If you have a metal shield, metal plate, it will shield because the current will be on the side where your source is, and the other side will have less, and it's an exponential thing. And when D divided by delta, and delta is the skin depth, they call it, where the current density is 1 divided by E, that's just a definition, that's where 92% of the energy goes. Then 5 deltas will give you about a factor of 100 reduction. So if you want a factor of 100 reduction, in decibels that would be 40 dB, you need 5 deltas. And delta is frequency dependent, so you can calculate it. Dependent on some more things, you need the conductivity of the metal, you need the magnetic properties, the permeability, you need the frequency. And then you can calculate this delta. And if you have 5 deltas, that's a factor of 100. So you can choose. And it's used in shielding theories. Skin effect. Okay, and this was the measurement. And here's where it tries to draw this current pattern. There's little current here, there's a lot here, and there's less here. So this depends on depending on the height, this is wider or narrower. So if you want to have it narrow, then put the cable down. If you put another cable here, there's probably not much to see. If you put it here, this is the amount of field that you still couple. So the ratio of this and this would be your mutual induction. The ratio of the induction to mutual induction. So you can calculate your crosstalk more or less. There's really equations for it, but we don't do it here. Okay, magnetic field needs current. There's a wire in the middle here, and this is the wire. This is the tip of the arrow is coming this way. So going into the room, this is right corkscrew rule. You can calculate the magnetic field. If you want to know how much, you can use Ampere's law, which is also a derivation of Maxwell's law. I think this was there first, but okay. Maxwell put it together as an integral description. If you want to know the amount of magnetic field a distance r from an infinitely thin wire with the current I, you can use this equation. You divide the current by the circumference of this circle here, 2 pi r, and you get a number. And the further you go out, the lower the magnetic field will be. Okay, this is the signal current. Then you have a return, assuming you have a twin wire, 2 identical wires, which is the return, which has all the current. Then you see an identical pattern but going with the arrows the other way. So this is going into the paper, into the screen, and this is the end of the arrow we're looking at. And this is an animation trying to show you the magnetic field. You use radial lines to see magnetic fields. One more, and then we leave it outside the middle. So this is a twin wire, 2 wires close together with some current in it. Current in, going in and out. And you get this magnetic field. You see, as long as the wires are not concentric, it will never be 0. So a twin wire, like the one we used for our experiment, will always generate field. So if you use it for a wrong signal, you'll get magnetic fields and you can hear them on the radio. Okay. Next step. We have cables. We can shield them. Shielding cables is useful if you have high frequencies and you want defined impedance. Okay, shielded cables, any cable actually will have this. You can do 2 things. One is put a noise source on the return. So if you have this coax cable, you put a noise through this shield. And then you look at the inside, what remains of it. So you would do a crosstalk, do a short circuit on this side, and you measure the voltage on that side of the cable. And that noise voltage divided by this current, this noise current, we call transfer impedance. You also have to divide by the length of the cable. So you have ohms per meter. voltage divided by current and divided by the length of the cable. If you make it twice as long, you get twice as much. Transfer impedance. That's the way current is transferred into voltage. Or the other way. Here, it's the other way. You have the current here going through the cable. Intentional current going through the cable, so you shield it. And now you want to know how much of it will go to the screen and how much it will stay elsewhere, in the ground or other people, other cables. This is a superconductor. This is an ordinary real screen with resistance and inductance and everything. And you still want to know how much of this current will go back through the screen. And you hopefully everything will go through the screen, because otherwise it will be in somebody else's case. Okay. Coax is better than twin wires. We've seen that with the animation. There's another one here, which is a negative. So this is the coax, concentric, and everything stays inside. This is my twin wire. And here, you see, there's field. Now, assume you have a coax. You have a coax and you want to connect it somewhere. And then suddenly you say, hey, there's here these connection bars with screws, and now I cannot nicely interface my coax. So what I do, I take a wire here around my shield and put it into the next hole. Closed it. So these two wires are, there's an opening here. The opening they call a pigtail. And the pigtail transforms this into this. And this black one behind here, the cable with the repair work, that's actually a pigtail. So I make a little hole here in the screen and you put a wire around it, that's a pigtail. And it leaks. I've heard that on the radio. So this is a good way to destroy your cable. And it brings the transfer impedance up. When you do the examination and asks you what happens, will the transfer impedance be better, lower, higher, then you know. It goes up. Okay. Can you live with it? Well, you can take some measures. We'll come to that, back to that later, but I'll show you one here. You can take some measures to reduce the effect of a pigtail. Pigtails are sometimes unavoidable. You see them in construction there. Yeah? Yeah. Okay. Okay. So, here's my cables coming in, shielded cables with some wires inside, more than one wire. I have a noise current on them. It's either a current coming out of these wires and generated here, or it's coming out of the field and going over your sensitive wiring. That's most possible. There's a coupling here, inductive coupling between this noise current and these separate wires and the common mode current. So what I want to do is make a screen, sheet of screen, metal screen, where the cables are going through. Well, if you just have a metal screen, or a plastic screen, and you put these cables, nothing happens. The current will still scroll on the screen, go over your wires and come back to it. So what you should do is make a good connection here. So connect this metal screen to this shield, the shield of the cable. So you open up the cable plastic, you connect the metal plate to the shield. There's special devices for it. It's called EMC glands. They are there to connect your cable to your metal plate. And now the current will flow outside. It will not go over your pigtail. And the pigtail without a current over it is no problem. And even if this would generate some noise, it will go back here. So it will work both ways. This is what we call a current boundary. We get back to that a little later. 6 nodes. Current boundary. Yeah, take a break first.
Okay. I need my hands, so I will